right, how's everybody enjoying the show so far? Good? All right, I'll try to keep this animated because I know I'm the first talker after lunch. I know the blood sugar crash should be coming in about 5-10 minutes. I'm afraid to touch anything with the AV to make it brighter in here. So, were you here when I thought I was turning the lights up? This actually starts going up. And then once that starts happening, weird things happen with the AV. So rather than risk it, so far, knock on wood, the live stream has been going good. So yeah, I've been live streaming basically the whole morning and now the early afternoon. Probably going to do the next session after that, which we'll see. Tim's probably going to send out the links if you want to watch this all. If you go through and you're watching the live stream, or if you're watching the live stream right now, I was just pointing to the person who was watching on their laptop. But you'll see it says October 11th and October 12th. There's nothing happening tomorrow. It's just I chose the wrong file to show in the preview and the loops and stuff from last year. So don't panic. This is all there is. All right, so we're about 2 minutes from starting. So just so we're clear, we're going to talk about neural networks, but we're not going to cure cancer. We're not going to create a computer vision system. Sorry, that's a little bit much for 60 minutes. I need at least 75 minutes to do that. I'm going to talk about the basic mathematical underpinnings of neural networks, what makes them special, and that's it. Don't worry, I hated math as a kid. I only started liking math about 4 or 5 years ago. But that's a whole other story. So how many people here have heard of neural networks? Okay, that's good. How many people really have a good understanding of how they work? Say, all right, one person. You may be a little bored. So you come for the talk, stay for the jokes, right? So neural networks are one of those things that is, I don't know, it's a little too loud, widely used term, but very few people really understand it. And for me, I had an aha moment when I was taking an online class, there's a link to that in the slides, where I finally got it. It finally clicked in my head. And that aha moment, I wanted to kind of put in a bottle and sell or share, right, as widely as possible. Because I think it's important because they are pretty impressive for what they do. They're actually simple structures, but they can be very kind of complex. So I'm Frank La Vigne. I'm a cloud solution architect here at Microsoft. I have way too many URLs, but franksworld.com and datadriven.tv are the important ones. That is my podcast, Data Driven, and we will be, over the course of next week, slicing these talks up into different podcast episodes. So, or you can go to Facebook, Data Driven Facebook, and watch it live immediately. There's a link on Frank's World, or Tim will send it around too. So I originally wanted to call this talk something like neural networks, what do they know? Do they know things? Let's find out. And usually I can tell who the BoJack Horseman fans are based on that. There's a whole thing in that, but highly recommend that show. I already mentioned my podcast. How many people here know that MSDN is closing up shop next month? How many people here heard of MSDN? Okay. How many people here have ever used magazines or heard of magazines? Okay. As I get older and the crowds get younger, that's more and more of a problem, which is probably why it's ceasing production. But I actually have this talk originated from the online class, but I also converted it to 2 articles, aka.ms/frankmsdn. These are from February and March or April. And I say I'm working on these 2 books, but here's the cool thing, right? I'm going to self-publish these, right? Last time I wrote a book, I had a publisher, and they annoyed the living you-know-what out of me. Because they were always insistent on, you have to get this chapter done by this date, this date, this date, this date. So I got my book deal in March, found out that my first son was on his way in April. Right, so the whole process of writing that book was tied into that. It actually was 10 years ago, right about now, that I was wrapping up the book. So yeah, I say that, but I'm self-publishing, so that all the pressure is on me, and it's just like, too many squirrels running by, I guess. Recently, probably my biggest project so far this year's side project has been this idea of a virtual summit. Most people in our field have not heard of this concept of a virtual summit, but you can think of them as kind of like back-to-back webinars, right? And it's basically like a summit like this, but you don't have to go anywhere. As a result, it's much cheaper to throw and run these. And if you use this discount code, it's actually less than $20. All right, that's it for the commercial part of this. This is the training I took. It's on edx.org. IBM has, if you look at that, there's 5 courses. You don't have to get the, you don't have to pay to get the thing, to access the content, but if you want to get the certificate, you can. And I'm not through all of those. I did the first 2, but it was really the first one where you kind of basically build out a neural network by hand in Python. It makes a lot of sense. All right, so we are at an age where practical AI is no longer science fiction. When I was a kid, it really wasn't that long ago, although the first 2 digits of every year were 19, AI was stuff of science fiction, right? And when I got to college, I was excited because one of my professors worked on artificial intelligence, right? That was his area of expertise. When I finally did take the class with him, because you always have requisites you have to take beforehand, I was kind of disappointed to find out it was Prolog, right? So Prolog is this language that, if you never heard of it, there's probably a good reason for it, but it was called artificial intelligence, but essentially it kind of did its own inference. But now we have things like computer vision. This is our API, and it took that picture with my webcam. It actually did the OCR on the writing on the coffee cup, and you see that it is 81% certain I'm a man wearing glasses and smiling at the camera. I don't know if that's really a smile, but I'll take it. But that was all computer generated, right? That's from a trained neural network. How many people here have heard of deep fakes, right? Interesting stuff. I highly recommend you go to YouTube and search Full House of Mustaches. That's like nightmare fuel. Right? To see the male characters is kind of almost believable, but when they're all together in a group, it's a little creepy. When you see the little baby, oh. Speaking of nightmare fuel, you've probably seen this. These were all done with neural networks. And a particular type of neural network called generative adversarial neural network. We're not going to go into this. You're not going to learn to use deep fakes today. Sorry. But when you look up how a neural network works, or what a neural network is, you see this. How many people have looked that up and seen this, right? What's this about? Like, what's going on here, right? How can this put Steve Buscemi's face on Jennifer Lawrence, right? How can this do computer vision? How can this do all these things? It doesn't make any sense at all. How does the structure work? Why does it work, right? And most of the time, for up until January, I just took it on faith that it worked, right? You put stuff in, magic happens, and you get an answer that's somewhat intelligible. But it wasn't until, I mean, this was really my reaction, actually. Most of the time, it kind of looked like magic to me. And whenever I hear that word magic, I think of this quote, right? Any sufficiently advanced technology is indistinguishable from magic. But it's not magic, it's math, right? And we're going to go into kind of how these little data structures, for lack of a better term, can come up with things entirely on their own, good, bad, and indifferent, and sometimes just plain weird. Now it's basically inspired by biology, right? We have, or at least most people have, a brain between their ears. You wouldn't know it sometimes. But your brain consists of billions of these. These are nerve cells. And each one of these nerve cells, I have my fancy 3D graphics here, consists of this. You basically have the body of it, and you have the input, and then you have the output that connects to the neurons. I don't know what the exact number is, but it's something like tens of trillions, a lot, right? So you have more connections between your neurons than you have neurons. So taking a closer look at this is basically the direction of the data, right? So there's, or the information of the message. You have dendrites, right? They connect to other networks, and they process something inside the nucleus, inside the body, or if you want to use the Latin term, soma, and then that goes out to the terminals that then connect to other networks, right? And essentially, I'm sure it's more complicated than this. I'm not a neurologist, never even played one on TV, and I didn't stay at a Holiday Inn last night. Basically, they fire or they don't fire, right? On their own, they don't really do much. But what's interesting is how this was kind of done is that this gentleman here, Santiago Romani Cajal, basically took, it's really gross, right? Something you want to hear right after lunch. He took thin slices of brain and kind of looked at brain tissue under a microscope, and he discovered these structures. Now here's the cool thing. Put it on its side. It starts to look a little familiar. Right? Kind of. Now, there's always somebody that points out that, well, neural networks aren't really how the brain works, right? That's true. They're really based on what neuroscientists thought in the 80s how brains work, right? I think they actually work with fly brains, and that basically was the inspiration for this type of network, which is called a perceptron, and that's kind of what we'll be building. So what's interesting about artificial neural networks is they are modeled after biological neural networks. Not a perfect match, but close enough. They have activation functions, and that's just a fancy way of saying neuron's going to fire or it's not, right? In the brain, it's electrochemical. Here, it's more mathematical, logical. The pros are you have amazing results, right? If you count putting Nick Offerman's face in a toddler, that's amazing. Or the things that we come out with it are pretty amazing. Cons are there's really no explainability. No one's really sure how they come up with their answers. And there's a whole lot of field of research kind of opening that up. Because right now you can't use neural networks in certain regulated industries because of that reason. You can't explain, hey, why was this person denied a mortgage? And apparently regulators go like, I don't know, neural networks are narrow, right? They are computationally expensive, and we'll see that in a minute. They all are also very complex. But they're based on very simple concepts. So does that make sense? So, we saw what a biological neuron looks like. This is what an artificial neuron looks like. So, how many people remember algebra or like math and middle school math? How many people have fond memories? Yeah, very few people. Congratulations, you're like the first person ever. I know I hated math at that age, but basically what's happening here is you have X as the input, X1 and X2 are two inputs. They go into one neuron. That circle there is the neuron. Those individual connections are then weighted, and you have a bias also attached to that. So you basically have 5 inputs per neuron. Okay? Then you see that Z, and then a formula. Z is the value of all those, the input and the weights, plus the other input and the weight, plus the bias. Now, don't worry about that word yet. It's not bias in the way you're thinking. It's more, think of it like turning up the volume, right? Turning up the gain on the stereo or something like that. Then, if you do that, you want to get a number between, say, 1 and 0 or negative 1 and 1. That's what the activation function is. And that's what A is. So you feed, that really shouldn't be an equal, that should be function, right? So you pass Z to a function, and you should get a nice compact value. Now, the most simplest one is this one called the sigmoid. And don't worry, this is not on the test later. Nothing to do with this guy, apparently. But basically, if you get a very large number, it produces a number close to 1. If you give it a very small number, it produces a number above 0, right? So that's kind of the key here of the math. So right now, you're probably thinking, great, I have to go back in time, probably this middle school trauma or college trauma. Don't worry, it's not that complicated. But what you do have to keep in mind, because there is a little teeny bit of calculus here, remember this graphic. What this graphic is saying is, remember the weights that we had, right? You had the input value, and then you had the weight attached to it. You can't change the input value, because that's changing what you're seeing or what the neural network is getting. But you can change the weights and the bias. So the weight is, you want to get your neural network to have a very low error rate, right? So that represents the error weight, errors, right? So if you give it too much weight, you start getting more errors. If you give it too little, you start getting more errors, right? So you want to find that just right. That's the lowest point. So you want to find the lowest point where you adjust your weights to that. If it doesn't make sense, that's okay. But keep in mind, this is what the same concept is in 3D, right? So basically, you're trying to find out where the error is the lowest. But keep this image in mind, because we'll kind of refer to that. Is everyone with me so far? All right. All right, so this is a small neural network. So how many people here have heard of the MNIST, right? If you studied this stuff, you probably was wondering, it's like hello world for neural networks, right? Basically, in the 90s or something like that, Jan LeCun, there was an RFP or a research challenge so the post office can automate reading zip code numbers, right? And it was a great problem set because zip codes are 5 digits long, or let's say +4, 9, and the characters are 0 to 9, right? So you have 10 possible outcomes. So a really bad one would be right at least randomly 10% of the time. Congratulations. So it's a really nice problem. So what they did is they created this data set of handwritten letters, right? Tens of thousands, say, and it's been shrunk down to 28 by 28 pixels. And which, if you don't want to do the math in your head, that equates to 784 pixels total. 74 in terms of the neural network, right? The first input neuron, or first level of input, is 784, one value for each pixel. And that value is going to be between 0 and 255, 0 being black and then 255 being white, right? That's how color we're encoding. Remember, this is monochromatic, so it's all grayscale. If you want to add a color channel, I'm going to need that extra 15, 20 minutes. But it's essentially the same concept where every color channel becomes a 255, 0 to 255 value. All right, so in a small neural network, I created, say, a second layer, a hidden layer, right? So if you think of that diagram that looks really like the sticks and the circles, those are what you call a hidden layer, right? Hidden in the sense you don't see it. You can always investigate it and see what the value is, but very often, most of the time, it doesn't make sense how it comes to the conclusions that it comes to. That gets into explainable AI, which is probably the topic of another talk. All right, so in the final layer, remember, 32, 32. So I have 784 in the input layer. First hidden layer is 32. Second one is, that's a typo there, right? So 32. And then the final one, right, the output is going to be between 0 and 9, right? So 10. So how many connections or how many multiplications do you think I have to do, right? And your first instinct is probably like, well, 784 times 32 times 32 times 32 times 10. No, there's actually more to that because remember the weights are in there. So every neuron gets 5 values. So I'll save you the effort. A small neural network consists of 26,506 adjustable values. And we'll see more of this, but that's really the key. So another way to think about it, how many people here are software developers or software engineers? Okay. If you're not, how many people have written code ever in their life? Okay. You know what a function is, right? You pass a function, right? How many functions do you, how many parameters do your functions typically have? 3, 4, anything more than 10, you go talk to the person who wrote it, right? And I mean, talk to them in a Jersey kind of way. So think of it like this, right? A cheap transistor radio. And before Spotify kids, that's what people apparently listen to. Free wireless too, unlimited streaming. It's pretty cool.
Actually, they were a little smaller.
They did make smaller ones, yeah, but that was like the iPod of the day. This is more Apple HomePod. That's it. So that is analogous to, you pretty much have 3 functions there, or 2. Tuning and volume, right? You change the frequency, right? So think of that as 2 parameters. Now, the neural network, you think of that 25,000 adjustable values, 26,000 adjustable values. You think of those each as little parameters. Well, then you get something a little bit more fixed. Which one of these lets you tackle more complicated problems? It makes a lot of sense if you think of each one of those dialing the knobs, and you have a lot more control surface in terms of what to adjust. Does that make sense? And I zoom in on that just because it's a pretty cool piece of equipment. All right, so with that, it's time for some code and demo. But here's the example of the MNIST data set kind of printed out, right? Because ones can be drawn straight lines, a little bit crooked. You see 6 here has stuff filled in. It's very messy in terms of consistency, right? Because that's just the real world, right? A picture of a cat is a picture of a cat, but it could be at different angles, right? And you'll see that the more data you can train a neural network on, the better the final results will be. All right. With that, I'll show you this. All right. This here is a visualization of a neural network that works through MNIST. And what I'm going to draw here, and will kind of help you visualize this, although I probably should have started with code. I already went down this path. Let's do this. All right, so I'm going to draw a number. And because of a fancy touchscreen, I'm going to draw a number. So you'll see, did a pretty good job, right? It says the drawing shows me a little version of the drawing, and the first guess is 2, second guess is 4. Well, that's kind of weird. But how did it come to that conclusion, right? So what's cool about this visualization is it's 3D, and you can do all sorts of fun stuff with it. But you can actually mouse over it, and you can see the weights and the connections between those neural networks, right? So basically what happens is you tune the neural network, and we'll see how that works in a bit here. But basically, this neuron, this is the raw input, right? This is 300, I counted, seriously. Is 300, I did not count this one, but it's not, you click on, you hover over this, you click on it, and it'll tell you what the weighted input was, what the output was, and the calculation here is basically the activation function. And they're using an activation function called TANH. There's about 4 or 5, but that's one of them. All right, does that make sense so far? Apparently it's supposed to be somewhere. So if I click on this, you'll see this, the brighter the neuron is, the higher the value. The less bright, the lower the value. So you see this was positive 1.72. You see the input was 44.21, output is 1.72, right? So basically, high number in gets pushed down between 1 and actually 1 and 2 in that case.
Will that tool load any model and visualize it, or just pickle or whatever?
This tool does not. This is just an MNIST. But if you, it's from a university website. You probably could do it. But there's a lot of visualization tools like this for neural networks to make them more explainable. Now the catch is that, remember, this is a small neural network. If you're doing something that's vast, the one that basically powers Microsoft's computer vision is 300 layers deep. There's 300. Yeah, that would be some visualization.
Well, but just for little models, they're usually you're doing 2 or 3 hidden layers.
Right. So this has 2 hidden layers, right? So you have the input layer here, and this is the first hidden layer, second hidden layer. So you kind of see how this ties to each one of those, and it actually does a really cool visualization. All right. So let's go. I always like to say, don't tell my boss, because this is a Google site. This is TensorFlow Neural Network Playground. Another way you I just wanted to show you the overall concept, then we can dig down into the code and see how it works. So this is called the Neural Network Playground. This basically is running a neural network in TensorFlow.js, TensorFlow being a framework for building and managing neural networks. and entirely JavaScript, and this is going to be a classification problem, right? It's orange or it's blue. And if I hit play, it's going to go through and try to figure out how to interpret that shape. And you'll see it'll learn it over time. And if you keep your eye right here, you'll see it'll actually graph the loss, right? So the loss is, remember, we want to get to that lowest point in the curve, and you'll see it'll try to get lower and lower and lower. So we're going to start it off, and you'll see it'll kind of start and then it'll dip. Ideally, we want to get to 0, but that's never going to happen, so we get real close to 0. I'm going to run that. All right, so you see it did it pretty quick. That's not much of a challenge, so let's pick something a little more complicated so you can watch it kind of work on it. There you go. So it had to go through that 90 times, adjusting every possible tweak there. Not a lot here, right? So there's, there's 2 hidden layers and there's only 6 neurons in there. So it's not going to be 25,000, it's going to be a lot smaller. But you see it got it pretty quickly, right? So the test loss is basically in your test data, and the training loss, which you figured out in training, was, in 0.7. So pretty close to 0. But you see there was that moment where it really was struggling, then it adjusted all those values. So let's try looking at some of these parameters here. I'm going to keep the activation layer here. So learning rate, right? I'm a developer, right? So and I like, cars, so I'm like, learning rate, that sounds like horsepower. When I crank that up, what do you think is going to happen if I crank that up to a high number? Good things or bad things?
It's going to be error.
It's not going to do what I thought it would, right? All right, so let's crank that up to 10. Sorry, it's Final Cut 10. There's no 11.
It would overfit.
No, I would be lucky if it overfit. Boom. So it started doing really well, and then boom. And the reason why is because, go back to that slide, the learning rate equates to these little green arrows, right? So if the learning rate is really big, I'm going to increase my weights, so I'll jump to this side of the curve. Oh, I'm off again. How off am I? I'll go, make those arrows become bigger. If the arrows are small, it'll take you forever to get to a particular minimum. So you want to pick a nice medium number. This is more art than science. So you get a nice resolution of finding that lowest value. Does that make sense? Okay. So we can play around with this. Let's give it something a little more complicated, like this. Let's add a few hidden neurons. And keep it 23. Yeah.
I kind of missed the part about the, I didn't really understand what you were saying about the underpinnings.
Oh, okay.
I was distracted because you said those are green arrows and they look brown. So.
Oh, yeah, it's a projector. Okay, so these arrows represent the distance there is your learning rate. So let's just say, first time I run my neural network, I'm here. Well, I want to see if I can do better, arrow-wise, right? If I have a really long arrow here, I'm going to jump over here on the curve. Yeah, it's better than one step. And if I do it again, because my learning rate is so long, I'll end up back here. So I'll never really hit that unless I'm very lucky. If these are small, like really tiny, heading in the right direction like this.
Okay, so it's just like a mean.
Yes, it's kind of like a mean. Ultimately, you're trying to figure out your gradient. That's descent, right? So you'll hear this fancy term called stochastic gradient descent, which when I first heard it was like, is that some kind of medical procedure? Gradient descent means basically this: you try to find a low point, right? And the lowest point you can imagine, if you will, here, which represents your error, right? So this I'm really wrong, this I'm a little bit less wrong, this I'm the most right I'm ever going to get. This is right all the time. So if I have an arrow that's too small, I can be here all day, right? if I have an arrow that's too much, I'll overshoot the goal. I'll never get that resolution, get down to the lowest point. So I kind of have to adjust that, and I can find that.
So is that against time? If it's just about the obviously great, so like if somebody's running things quicker, they're not really absorbing that much information. They're just.
It's kind of like that, although it's very easy to take these neural networks and make them anthropomorphize them. That's my $10 word a day, right? Make them think like they're people. They're not. The more complex, I guess, you'll see some, similar behavior, but it's kind of like that. It is kind of like that. You want to figure out where the lowest point is, right? So, say you want to find out. You're looking at a picture. And the picture is really pixelated. You're not going to find out much detail. In this very fine grain, you'll find all the detail, but sometimes it's too much. Does that make sense? So that's kind of like that, yeah.
So your learning rate is kind of like your relaxation factor, and
it sounds about right. Is that like a mathematical thing? It's very similar to that. Yeah, ultimately, it is a lot like that. That's where my knowledge of math kind of trails off. But basically, you're trying to, if you're thinking about derivatives, the smaller the distance is, the more accurate you'll get. Now, in calculus, you want to get like to next to nothing. In practical terms, you don't want to do that because it'll take forever. Right? So, is that 0.01% of accuracy worth $10,000 worth of compute time? Not.
Can you relate it to the weights?
So these are the weights that you're adjusting.
Okay.
So I increase the weight. My cost function, right, that's not cost of money. Cost function is another word for loss, right? How accurate it is. So if I increase the weight on one of those inputs on the neuron, it's going to be wrong, right? So now I'll take it back a bit. Am I better? Yeah, I'm better. Can I do better again? And I'll take it back to this way. So it turns out it's probably more visible here. Turns out the slope of the line, or the orientation of the slope, gives you an indication of what direction to go in. And if I lost you, that's okay. It took me 30 times to hearing that same sentence before it clicked.
Yeah.
But does that make sense?
I get it because.
Right, because So if it starts like tapering off, then okay, it's time to I'm getting close to the end. Maybe. Because you have this notion of local minima and maximum. Global minimum. Which, how many people here have I lost so far, right? No one wants to admit it? All right. So, local minima is the idea. I want to find the lowest point on the curve. But what if the curve looks like this, right? Looks like a roller coaster. If I drop a basketball, it rolls down to the bottom. Well, that's the lowest point, right? Well, the lowest point local to me. But what about the lowest point in the entire ride? It takes a lot more work to figure that one out. This is the type of thing, I'm told, that keeps mathematicians up at night, because there's no good answer to get the global minimum. So if you're having another trouble, you can imagine the lowest point in this room, right? It's pretty easy to figure out. It's probably the outwards, right? Where's the lowest point in Reston, right? And one, you can answer that just by looking around. The other one, you probably have to go to the USGS and figure out what the lowest point in Reston is. That make sense? But that's way more, but that's kind of how a neural network is trained. All right, so with that, I'll show you some code. All right, so this is a Jupyter Notebook that I have. How many people here are familiar with Jupyter Notebooks? Okay, cool. If you're not familiar with Jupyter Notebooks, they are awesome. You will hate them the first week. It's kind of like the VI editor, right? How many people here know what I'm talking about in the VI editor, right? Did you love it, your first experience with the VI editor? No. Did you eventually first tolerate it, then accept it, then love it? Right? Yeah, eventually. Less people, but somebody did love it. I'm not the only one. All right, so this is a tool where basically I don't have to install anything locally. I go to a browser. I'm running code that's attached to a Python kernel, in this case. And I'm going to run each one of these cells independently. All right, so what you see here is x1, x2, right? Those are the input values, right? W1, W2 are the weights. And then the bias is 0.03. I picked these completely random. And then what I'm going to do is I'm going to run that formula that we saw in the middle of that circle. And I'm going to print it out. So now with notebooks, they typically cache what's in there. Sometimes that's good, that's not that bad. But just for fun, I ran that cell, Shift Enter, or hit play to run the cell. All right, so now I'm going to start pulling in. How many people here are Python coders? Okay, cool. How many people have never seen Python in their life? All right, well, that's good. If you know C#, Java, it's pretty much mostly the same thing, right? Don't get alarmed if there's no semicolons, right? No laugh on that one, that's interesting. So this is my Sigmoid activation function. If you remember, I had return 1 over 1 plus the e times whatever. We can look at the slide again. And then I call that, right? So I take that 2.3 and then I squish it down to a number between 0 and 1. The output is 0.89. So just to prove, I'll give it a really big number and a really small number. And you'll see it comes between a number between 1 and 0, right? So you're going to give it an activation between whatever goes in, you're going to get a number between 1 and 0 on the other end. That make sense? All right, so what this is here, this is kind of like the MacGyver duct tape version of Keras right here. All in one cell. Set your expectations accordingly. So what this is going to do is basically going to create a structure, or allow me to just create a structure of nodes with those values, the weights, the biases, the inputs, the outputs, right? And it lets me have a nice little description here. On that. So I'm going to create a neural network. 784 inputs. Right, that's 28 times 28. I'm going to have 2 hidden layers. Here's my array of 2 hidden layers, right? 32 and 32. My output is going to be 10. So what this is going to do, this is going to print out the structure that made for me. It's JSON, actually. Does that make sense so far? So that structure that you see with the circles and the dots, that's basically what this is. But I set it to kind of random weights in the beginning. Just to kind of set it. And what I'm going to do is I have the calculated weighted sum. That's the function. And setting that, the inputs of the network, to these values. So we could pretend those are pixel values, right, in terms of brightness. Then I'm going to calculate the weighted sum for that particular node, right? So I'm going to pick this node here, the first node of the first layer. So the first little circle, top left circle. And I'm going to figure that out, and I'm going to figure out what the bias is. I'm going to print that out. And I'm going to come up with a weighted sum for that. And the weighted sum is 2.74. Now, it's not between 0 and 1, right? So now what do I need to do? Sigmoid. Put it through the activation function, exactly. So now I'm going to compress it. And the value is 0.94, which means on all intents and purposes the neuron will fire, because it's over a certain point. We did this 26,000 more times. We have our first run through the network. First run. How many epochs did we see going through there? Hundreds? Thousands? Right? A lot of math there. Not complicated math per se. This is why GPUs are awesome. Because the GPU can do a lot of these in parallel, and it'll really speed up your neural network dramatically. Now, there are other things like GPUs and field programmable gateways. I'm not going to pretend I understand how they work. I know how GPU works. Ultimately, this becomes a linear algebra problem, and you can do those matrix math much more efficiently across a GPU than you could a CPU, which is why GPUs can run through this training really quick. Everybody with me so far? Good. All right. So that was kind of like how to like the little circuit that kids had as a kid or whatever. Like I didn't have as a kid, but I got it from my kids, where you build like a little radio transistor or something like that. My kid made one that made rude noises, so go figure. But this is how that was kind of like building your own. This is how it's actually done, kind of more in professional production. You use these libraries, TensorFlow and Keras. And what's going to happen here? And I don't know how I'm good on time, but if I were to run this, I want to walk through it, then I'll run it, and I'll show you some other demos. And hopefully, because this is not tied to a GPU. When I do customer demos, I run them in parallel. I do a GPU one, not GPU one. I start down. I set up a GPU, and I run it on the GPU, and the GPU figures it out, and then poof, go back to the other one. The other one just finishes. Basically, what I'm doing is imports. I'm importing from Keras. Keras is a kind of a nice front end to a back end learning system like TensorFlow. You have a question? Or no? You just itches. Okay. Then I'm going to download the sample data, right? Which is all the GIFs of graphics of. All right. If you're not familiar with Jupyter Notebooks, this means it's still running. This kernel busy. When that clears up, that means I can run again. That star means that's the cell that's either queued or running right now. I could be lazy and say run them all. But again, as I'm getting this close to the end of the presentation, I want to be careful. Because some of this could take a while. All right, so once I download the data, I can print the shape of the data, right? So I have 60,000 records for training and 10,000 for testing, right? Everybody familiar with that data science thing where you split your data into like 60-30 or whatever? Okay, you're doing the same thing, all right? And then I'm just gonna show on the screen. Here we go. So there's downloaded data, and we'll see here. I'm just gonna print one of those images. Come on. All right, now that it's come back. Somebody give me a number between 1 and 60,000. No one? What? 49,375. Right? So that's the image, that's that one, right? So that there's a whole series of images that just downloaded. Right? And test, let's see, test, I need a number between 0 and 10,000. Or 999. You know it. That one?
874.
There you go. So what this is going to do is going to flatten into one-dimensional layer, right? So I'm taking all that pixel grid that you see in the pictures, and I'm basically saying row, 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 row your book now. And what I'm doing is I'm converting it basically to numbers, right? So you see this structure here, all right? I'm going to flatten that image. All right. I'm going to divide it by 255, because that's grayscale, right? 0 to 55. All right, and what was that number here for this one? Train. All right, let's take a little bit longer to run. There we go. So this is the array that represents that. So if you can kind of use your imagination, right? 0 means there's no pixels there. The higher the numbers, the brighter the pixels. Right? So you see for a while there's nothing, and then suddenly there's a couple of things. Let's scroll up and kind of see, yeah, that's kind of true. So now I'm going to take the training data and the testing data and basically convert them to categories, right? So each one is going to be labeled, 0 to 1, 0 to 9. And then now This is a function I built, or a method that will build out the model for me, so like before. So what I'm saying here is I'm building a sequential model. I'm going to add a dense layer, and a dense layer in neural network terms means every node is connected. Every node in my current level is connected to every node in the next level. There were different types for different purposes, and I'm using an activation called ReLU, Rectified Linear Unit. It's different than Sigmoid, it's different than 10H. There's about 4 or 5, so you've seen 3 of them, and we'll get play in the playground if we have time. That sounds weird. To see each one has their own advantage. Sigmoid was the first one to come out, and it's typically the worst. ReLU is the most popular. Input shape is the number of pixels, right? Number of pixels, 784. I'm adding another dense layer, 100, and I'm adding final dense layer with something called an activation type of softmax, which will basically, if I have, say, it'll give me a percentage value that all adds up to 1. So if I'm splitting it into 10 parts, it'll give me something that all the values will add up to 1 and I pick the highest. Does that make sense? I know I didn't explain that great. Yeah? All right, softmax will give you like the percentage. So if you have 2 buckets, everything will add up to 100 or 1. If I have 10, everything adds up to 1. You know what I mean? So we'll go back to the 3D visualizer. You can kind of see the number looks like that. So remember, I have 10 total. So say if it'll be 80% positive, it's a 3. 1% positive, it's a 8. And then the remainder is split across the other probability. What's nice about that, 2 or 3 tend to rise to the top just from the get-go. All right, so then what I do is I do the compile, and I return the model. So this here calls that method, and I probably should have this in its own cell, so I'm defining the method right now. And this is what's going to take a while, and I'll let it run, so we can kind of see it happen in real time. But ultimately, model.fit is where it's going to do the training. And it's going to go back and forth across many, many epochs. And you'll see its accuracy improve, right? So we can kind of look at the canned one, but first it starts off with 96% accuracy, that's what it gets to. Then it goes 97, 98, 97. It's kind of stuck in 97 for a while, then it gets to 98. All right, so let's run this cell. Let's see what happens. So it's training. And I set it to 10 epochs. I could set up to 1,000, or we'd be here until tomorrow. But you'll see training on that, it's validating, it's still working on it. Still working on it. Not attached to a GPU, this is free compute, so it's kind of, you get whatever you get. But you'll see in about 10 minutes or so, it'll actually finish all this. But another 10 seconds or so, you'll see the report from the first epoch. And you'll see it kind of work through it. Eventually you get to an accuracy, there you go. So it took 42 seconds, 97% accuracy, now it's going to go through again, train it again, it'll get a little better, then a little better, a little better. Eventually this model I got to 98%, and what's cool, this has been a real kind of point of confusion for a lot of customers. I could save this model, right? I don't need a GPU for the model. Once the model is created, I know the exact weights and dials. And think of that switchboard. You need a sound engineer to figure out the best way to adjust every dial. You don't need a sound engineer to sing or talk into the mic. So that's kind of the analogy, is that once I save that model, I can have very low compute do that, right? I can save that model, rehydrate that. It's saved as an H5, but it can be saved as a pickle file, right? Some binary format. I can rehydrate that and run that on a Raspberry Pi, right? It doesn't need a lot of compute. You don't need 32 GPUs to run a model. If you're doing that, you're doing something wrong. So the gist of it is that most of the computer labor is done in the training, and the product is your H5, is your model. This is leading into some interesting scenarios because data scientists used to work kind of in isolation in their own parts of the building. now, as AI becomes more and more crucial to an enterprise, now they're becoming part of the DevOps story, right? Cool kids call that ML ops, right? Because they're not producing code, although they do produce code, clearly, right? Code is being made there. What really matters, the artifact, is that the right DevOps term, artifact? All right, the thing that matters is the model, right? So obviously there's pretty well-worn paths to checking in code and versioning and all that, but the model is the thing that has to go forward, has to get thrown over the wall, like the guy said earlier today. I think he's in the room. So you throw it over the wall, so to speak, you throw the model over the wall, and that's what you deploy. So how that looks like, you basically reload the model, and you can basically give it the code again. Does that make sense? Almost at time. I want to show you some things where you can really mess with the neural network. So here's a fun thing called Teachable Machine. Unfortunately, it's a Google site. And again, this is JavaScript. So what I'm going to do is I'm going to train it with just a few samples, and it's basically building out a computer vision neural network. And there's a really cool tutorial with a really funny video. But what it's going to do is I'm going to train it. I'm going to train it on condition green, we'll call it, right? And that's going to play a cat GIF because it's Google. And purple will be another condition that's going to show a dog, because I guess there are dog owners in Google too. And I don't know what this is, but it's a small furry creature, the third one. So this is just an example. So I'm going to teach it to recognize me, like that. And then I'm going to train it when I'm not there. So what you have now is a person detection system. What? Who wants to volunteer and stand in front of the camera? It actually will confuse us. Seriously. It looks for a person. Whoever wants to do it. No one? All right, come on. Just from the look. So before you do it, okay. I was going to say, what do you think about it? So it's a person detection program, right? So this is where volume of training data, we all look alike. I mean, no one would confuse us, right? Maybe just the glass, how about now? No? Okay. No one would confuse us. The neural network thinks it is, right? That's because I didn't train it. Now, if I train it on you, if you don't mind staying there, I train on you, all right? Now it knows 99% sure it's you, which is pretty reasonable. Now step out of the frame, and nobody's there. Now if I go back, let's see what happens. I should go back. Now let's try this. Stand next to me. Let's see what happens. You see that? You see that? It's freaking out. Yeah. Okay. I'm curious. I don't know what will happen. Though I suspect you don't have glasses. I don't know. What do you think? Do you think you'll think it's her, or do you think it'll think it's me? Wait. Neither. Well, neither is nobody. I think it's going to be confused. I think it's going to bias it slightly towards her because she doesn't have glasses. That's what I think. I don't know. That's what's great. It's science. You don't know until we try. Go. Give it a shot. Oh, right there. Yeah, thanks to with the 100% confidence on. But I bet if you had glasses on, I don't know. I really don't. Here's the thing. We don't know what the neural network decided was the differentiator. Right? So when you hear stories about bias in data and facial recognition systems, this is kind of it. They don't have enough. So weird things are going to pop up in ways we didn't imagine. So there's one story I heard. Again, some people say it's true, some people it's not. It's not really one of those legends. In the 80s, the DoD wanted to train neural networks in the 80s. Right? So they were doing this on mainframe. They wanted to train a neural network to detect tanks, right, in pictures. And I think you heard this story, right? So there's also some other stories that kind of attach to that, but let's not get sidetracked. So what they did was they trained it on a bunch of pictures, right? And they did the testing data. How well do you think it did in the testing data? Great. Stay with me though, it does turn terrible. So when, basically they couldn't believe it. So when they tested it out with real data, they discovered that there was a problem, right? So let me back up. When they created the sample test set, they only had the tank available for one day, which happened to be a sunny day, or no, it's an overcast day. When all the other pictures were just various weather conditions, right? Because they were thinking of that. So it turns out what they actually built was not a tank detector. They built an overcast day detector. So if it saw blue sky, oh no, there's no tank in there, right? But we don't know. It's like if you have kids or you have animals, right? I have dogs, and they know when the little one is done eating to run by him because they know. More so when he was a toddler, he would throw the food he was done at and watch the dogs jump and catch it because he thought it was funny. I certainly didn't teach the dogs to do that. I certainly didn't teach the kid that that's a good habit. Finally broke him of it. But that's that kind of like they learn kind of what they see and what motivates them, if you will. Right? So it's all about the training data can have a significant input or influence on the output. And this is something that you hear people talk about, ethics in this space, and your first thought is, that's not really a thing. And then you look at it and think, well, in this little example, I mean, I don't look like her, she doesn't look like me, and they don't look like each other. But yet it thought it was the same condition because I bet if somebody went up with pronounced, your glasses probably wouldn't work because my friends are too. But you're right. We don't know. It could be my shirt. Maybe. I mean, we don't know. That's the thing. We don't know.
Well, what about what you were saying about the part that you go over the wall? What if you go something over the wall and then have to do the...
Well, then, here's the thing, right? This is where the ethics come in, right? If you're talking about, I always say, like, if you throw this model, it's not perfect. And no model is going to be perfect. But let's just say has a severe problem of bias in it. You throw it over the wall. You think of people running the IT cert, no knock on the engineering folks, but they're not going to know, right? Who's hospitals going to find out? Now, if you're dealing with who's going to pay their phone bill on time or not, someone's going to die. If you're dealing with medical or where you can send police resources, that's serious stuff. People's lives could potentially be ruined. That's a bigger ethical thing. If T-Mobile says this guy's not going to, this guy's going to pay his bill mostly on time, but sometimes not, no one's going to die. I mean, somebody watching who works at T-Mobile, I'm sorry, matters to T-Mobile. I'm talking to the camera. Yeah.
If you threw it through your simple visualizer that you used earlier, do you think you'd see the features show up?
Probably. There's a lot of research being done in that kind of explainable AI, like, well, what made it do that? And a lot of that is just testing. If I did throw it to the visualizer, there's a really cool video, and I can't find it again. But supposedly, there's this really great 3D visualization that's even cooler than that. You can actually see hotspots where if you give it a particular bit of data, it'll show you what connections kind of light up. And that becomes more and more of a problem as, however many neural connections there were, 25,000, that's pretty easy to see. But if we're talking about millions of layers or hundreds of layers, then the visualization problem gets bigger. But you probably could see that. A lot of work's being done in that space. But the easiest thing to do for now is make sure you have a pretty wide array of training data, the best you can get your hands on, and then some.
Couldn't you build a neural network to analyze a neural network to a network to analyze the features on both of the two models to tell you if they're close or not?
Yes, you just described a generative adversarial network, basically. Kind of, although your purpose is a little different. But then you still have to know, what you don't know. You have to know what you're missing. And that's, how do you know what you don't know? You know that you may not know. Right? Somebody wants to do this whole thing. He did this whole, it was DevOps Dojo, right? And he did this whole wonderful presentation, but he was talking about different layers of ignorance. One, you don't know. You're completely, like level 0 is you think you know everything. First level is you think you may not know everything. Then you know, like it goes to like 5 levels, and basically it works out to you don't know that you don't know. But then there's one more step beyond that. You're not aware of that. You're not aware that you don't know everything. So basically, 2 things you can do to help prevent this from happening is be mindful that your data does not represent everything. It doesn't represent the universe. No model you can build, well, put it this way, if you can build a model that takes into account all the entropy in the known universe, you need to start a hedge fund. You know what I mean? Right? It's not going to happen. So you have to know that you don't know everything, and there's things that you may not. There was a Dilbert cartoon where the boss said, I want to know a list of specific unknowns we should look out for. But you can't. Right? The other thing is, that just knowing that alone, I think, is helpful, and knowing that the model is not reality, the model is a representation of reality. It could be wrong. Right? The problem is going to come mostly when people take AI at its word. Right? I mean, if it's 99% sure of something, well, I mean, it's 99% sure. There's a small chance. It's not impossible, it's improbable.
Wasn't it, like last couple weeks ago, Elon Musk and, was it Microsoft? They just announced they were going to do a general AI, and they invested billions of dollars in
general AI is a term for kind of like what you see on like C-3PO or Star Trek, right? Like, where it can handle general situations. We're some time away.
But they're saying they're going to throw billions into it to do it.
Well, I mean, it's going to take billions, trillions of dollars of research to make it happen. But you know, I'm not sure we'll see that in my lifetime. I'm not even sure I'll see it in my kids' lifetime. Grandkids, maybe. No, I'm serious. Like, it's so many. Even the most clueless person. So people get upset when I do this again. The most clueless person you know knows that gravity goes this way. Right? You know, we all have drive here pretty much, right? So how many people don't know how to use the turn signal? But they know gravity, right? They understand that, you know, they don't understand the theory of gravity or gravity waves and all that stuff, but they know that if they have something and they drop it, it's going to go this way, it's not going to go that way. There's certain, some people call it animal sense or like kind of that stuff that billions of years of evolution have kind of baked into us that we kind of know. And that is turning out to be a big problem for AI to kind of work through that. Will they get through it? Yeah, I just don't think. You know, I think it makes for great headlines. I love Elon, but he loves his headlines. He loves his crap.
Well, what you're saying is you're doubtful that their investment will turn out anything.
Well, it'll turn out something. I mean, you know, it'll turn out something. I'm glad you're moving in that direction. You're going to have good things happen, but you're not going to get there. You're not going to get to Oz or, I don't know, whatever. You're not going to have, like, C-3PO walking around.
Kind of like we sent a man to the moon, we got all the computers and everything.
Right.
So,
You're right, exactly. Like, was the moon program worth it? I mean, you can argue that as the day is long. I'll get to your question, I promise. But the computers were an offshoot now because people thought, you know, the head of IBM in the 60s said there's a market of maybe 4 or 5 computers. Somebody once said that 640K should be enough for anyone. Right? Now he's a billionaire fixing malaria, right? I mean, people say things that are stupid and it's kind of funny. I mean, not funny, but you have a question.
So there was this Russian face app that's going around.
Deep fakes?
Huh?
Russian face?
Face app.
Yes, the thing that made you old and stuff?
Yeah, or a woman or a person.
Right.
Whatever. So, what was it? Because obviously that's AI.
Right.
So what, I guess my question is like, what is the, I don't know, logic behind that? Like, what is that advanced beyond like what?
More than this.
Yeah. I mean, obviously not more than this.
Right.
Like, is that, like, what is
So
the,
what it's doing, well, there's some concern over what the origin of that app was, because people basically gave them their face data that it can train their AI on. I don't know.
What does that even mean?
Well, what that means is once your face is scanned by one of these algorithms, it basically knows it finds 168 points on your face, like distance between this part of your mouth, this part of your mouth, distance between your eyes, things that are very hard to or impossible to change without plastic surgery. So you can basically, millions of people gave this obscure Russian company, PII, without realizing it. So they can train their models or sell, they'll probably do it, they'll sell the data to whoever wants it. So that way if somebody pops up later, like and they become famous later, they can be like, oh yeah, that person's face is on data. Because what you can do is you can basically boil down a picture, and if it does facial detection, it can, let's just say 68 points, or 50 points with the math there. 50 data points is pretty easy to figure out. And how that works, actually, I have a demo for that. Here's the face. Moved it. There we go. So I will take a picture. And actually, I think the other website. All right, so I'll take that picture. And you'll see those are some of the points that he uses to identify me in particular. Right here? Really? So I look on Facebook and I see people I went to high school with. I'm like, I'm just happy to have hair. I'm just seeing some of this business. Anyway, but you'll see, you get a pretty decent guess on the age. You'll see it measures that. So that little data set can represent me. And are there people that are close matches? Yeah, but no one's going to have exactly that match. It'll get close, but there's a certain, it'll narrow it down. That's why you see in Hong Kong going on right now, they always make sure they protect their face, or if they have to take off their mask, they use a laser thing, because the camera is not going to be able to.
Oh, that's why they're.
That's why they're doing the thing with the lasers to jam the cameras. Yeah. Pretty sad and amazing.
I was wondering if there are any ways that it can deal with like lighting. So like your hair looks brown, right? If you're in like dim lighting or something, or just training data, or
yeah, there's input data. That gets into a whole thing, and like depending on the lighting, my age can go down to like 20 and up to like 60, which depending on who you're demoing it to is really good. So I'm always very cautious about showing this to customers because some people get upset. But basically, so one of the things this does is that you see if you find those points, then what it'll actually do. Let's not get into the emotion one right now. But you'll see is that it knows what a face kind of should look like, and then it'll adjust. It'll figure out what my angle of my head is. That's how those Snapchat filters work. They do that, and you'll see once it loses a certain number of those points, it kind of breaks, and a little like puppy thing disappears on your face or whatever. My kids love them. So, all right, I think I'm out of time.